Okay, so let's try 37 because this illustrates a trick I was going to show you guys how to do anyway. So the directions on 37 say something bizarre. So let me just ignore them and try to solve this. This is going to last all of like 2 seconds. I should integrate from 0 to 1 and from e to the y to e, x over log x dy dx. Right? Which means the first thing I should try to do is integrate dy, right? Okay, that seems like pretty easy, right?
Yeah, just all that treated as a constant. It's not wild.
Okay, and also keep in mind the double integral trick, right? Seems like it should work here. But it doesn't because there's a y in the bounds of that first integral. You guys see that? Also, I hope I got the order wrong when I wrote this down, which I did.
Okay, I was going to say,
You guys see how I know I got the order wrong?
because there was a y.
Oh, because there's a y.
Because there's a y there. So the result, right, of integrating dy and then evaluating with a y in the bounds was going to be a function of y. And then I couldn't integrate that out, so I screwed it up. My bad. So now what I'm thinking I'm supposed to do is I'm supposed to integrate dx, x over log x. And Chris is telling me that he doesn't recall the trick for how to integrate x over log x.
Wait,
The
isn't that natural law?
distribution u equals 1 over.
So I would personally, if I was going to do something, I would try integration by parts. You guys see that? If I was going to try something, but I'm not, because I'm going to do the thing the book suggests, which is give up on this and switch the order around. You guys see that? So the first thing you need to do to switch the order, which is a crucial trick, is to draw the region you're integrating over. You guys see this? So I'm integrating over some region in the xy plane, right? What region is it?
Y is a
1.
Yeah, so I know the y's live between 0 and 1, right? Okay, so the y's live between 0 and 1. And then where do the x's live?
From e to the y to e.
Okay, so they live...
Oh, from e to the
This
0 to
rectangular
e.
then, if you have a y in your x.
Yeah, good. This isn't a rectangle. You guys all see that? Because this guy's making this not a rectangle. Okay, so this is my starting point, right? That x is e to the y. And I'm going to x is e, right?
Oh,
X is e is a pretty easy place to peg. That's something like here. Like there's 1 and 2, and then 3 is a little bit past this. And here's my other two bounds, right? This is y is 1, and y is 0 is this guy. So right now I've kind of narrowed this down to this box, right? That points off in this direction. But there's some kind of a left edge to the thing I'm integrating, and it's this.
Y is never. Oh,
So that's x is e to the y.
and y begins at 0.
You guys see that?
That's it, Y is natural.
And y ranges between 0 and 1, right?
Correct.
You guys see that? Okay, so some of you're probably having a hard time visualizing this thing, right?
Yeah.
Okay, so if this was a normal, like everyday Calc 1 thing, this would be y is e to the x, right? So let me solve for y, because that's not what's going on here, right? They're switched.
Okay.
Okay, so if I solve for y, what's y?
Natural log of x.
Natural log of x. oh, I know what the natural log of x looks like. Right? No? Okay, how about this? Do you know what e to the x looks like?
Natural log of x. Yeah.
So here's y is e to the x, and you need the inverse to this, right?
Mirrored across y to the.
So you make the line y equals x, and then you mirror this picture, so you get something like this.
Is that intersection on the x-axis going to be in our bound? Or that's one?
It's going to be interesting. And then, what's the other guy?
And then at e, it's going to be at a height of 1. So.
Yeah. When you put in e to this, right, the log of e is 1. So I know it goes through those 2 points, and it looks like, well, it looks like an exponential curve on its side, right? So it looks something like that. If I filled in the rest of it, this would be y equals log x, which is the same thing as e to the y is x. You guys see that? When you're doing this trick, you have to be a little careful with your plus and minuses. This one's easy, right? Because this equation actually does mean this equation. Right? Because this is actually an inverse function. But if you like unsquare something in this process, that's not actually got an inverse function. Or if you arctangent something, right? You need to be careful there. Because those aren't honest inverse functions. So now how do I switch my order of integration? I want to take the thing I started with and rewrite it as a double integral. The function's not going to be different, right? But my order is going to be different. I want to go dy dx. Yeah, so don't just switch these. If you just swapped these guys, right, you'd end up with a y in your outside evaluation. So you'd end up with a function of y. Like this thing here is categorically a number, right? If you just willy-nilly switch the bounds, don't do this. You would think this is the integral e to the y to e, and the integral from 0 to 1 of x over log x dy dx, right? But this thing here makes this guy a function of y in the end.
That violates Fubini's theorem though, right? It says you can always flip them.
Fubini says on a rectangle you can always
Oh,
flip
okay.
them. On a not rectangle you have to be careful. So, yeah, Fubini's could be rephrased as you can always flip them provided you can do this trick right. Which is why Fubini's doesn't say that. Fubini says on a rectangle you can flip them. You guys see that? Okay, so what do I put in my bounds to actually get this sucker to work? So let's see, where do my y's vary in this? Which region am I talking about here?
The inside part.
Like this stuff, right? So where do my y's vary?
Oh, so now that you're squishing it this
My
way.
y's go from 0 to ln x. You guys with that? And then where do the x's range? 1 to e. You guys see that? So Fubini's could say, right? You can switch them as long as you think. But that's too vague. Cool? So how do you do this now?
Now would you break it up into parts? Into
Oh.
different parts?
You just the
Just
first one,
integrate,
you just
right?
add a y to it.
This thing's constant with respect to y.
Yeah, so you just add a y to it.
So you just slap a y on there. So you got the integral from 1 to e of xy over log of x evaluated from
ln x to 0.
Yeah, 0 into ln x.
0 to ln x, right? And those are y's, right? And then we should be integrating the result dx. You guys see this? Okay, so what am I going to get out of this categorically?
X.
This thing's going to be a function of x. And then out of this, I'm going to get a number. Good, that's good, right? I'm in number land, which I'm supposed to be in. Okay, so once you do this evaluation, you're integrating from 1 to e what? X, right?
Dx.
Dx.
Well.
Good, yeah?
Yep.
Okay. And you get
E squared over 2 minus 1/2.
e squared over 2 minus 1/2. Which, just for kicks, just because I can, that's e squared minus 1 over 2. And the top is difference of squares. So that's e plus 1 times e minus 1.
Oh.
I don't know why, it just looks really slick like that. Any one of those is fine. You guys cool with this? Did that trick make sense? Like how that could be handy? Because that first thing's a disaster, right? Like Chris spent how many hours? I have no idea. Not reading the directions. You guys see that? So if something seems impossible, it could be. Write the region down. See if you can flip it. It's a cool trick to know. Questions, deals?
So there's no fancy trick to know when this should
This is a good, like, of last resort thing.
Okay.
Like, you set up this integral, you try it, just banging your head against a wall trying to figure out how to integrate x over log x, right? Like, the first thing you'd try is you'd say, okay, do I recognize that thing? No. Next thing you'd try, is there a u substitution that's going to work here for me? No. Yeah. Right? What's the u substitution you'd try?
U equals 1 to log of x.
Yeah, you try u is log x, right? Then du is 1 over x dx. You've got the dx, fine. But the 1 over x, you're kind of missing. You've got an x, not a 1 over x. So you're sort of screwed.
You could work out the integral then if you made u.
Now, you just kind of can't make that to work, right? So you could try for a while. There's a couple cool tricks you could try. None of it's really going to get you anywhere.
Is that one not?
Then you might try integration by parts, which is a terrible idea, but might actually get you somewhere. I don't know. I'm not going to try it because it's like a giant gobbledy mess.
Sounds like it might go forever.
Yeah,
Well,
it
you have to do
might.
it twice.
It might be one of the ones. It's not one of the ones that you do twice and then solve. You guys remember that trick?
It's not that one?
It's not that one.
Oh.
So yeah, it's kind of a mess. Like you try a couple of things. If it all seems like it's gone to hell, try this. Worst case, this is yet another technique that didn't work, right? Best case, it works. What do you do after this technique doesn't work? Like after you've tried several things and this doesn't work, you...
Distribution is one.
I would just do a Taylor approximation and then try and integrate that.
No, F that, no.
Substitute.
No, God, no, don't. So there is a place for that, and it's not in this class because you have to be a little careful. And I don't want to have to try to explain when you have to be careful and when you don't. So it's not a terrible idea to try to construct a Taylor polynomial. This is a shitty candidate for constructing a Taylor polynomial because you've got an x on the top, and the thing you know how to construct a Taylor polynomial for is going to be on the bottom. So you're going to divide a first degree polynomial by an infinite degree polynomial, which is going to be a massive pain in the ass. If this was flipped over,
That'd be great.
then the Taylor poly approach would work, but so would the U substitution
Yep,
approach.
your substitution works so much better if this was
You
flipped.
guys see that?
Yeah.
So like, what's your next thing after you've tried all the techniques you know?
Wolfram Alpha.
Yeah, go to Wolfram Alpha. Plug this
Like-
into Wolfram Alpha.
Like I said, panic because you're on a test and you can't do that.
You can write, I would integrate this numerically. I don't know how to do this with the techniques I have. Like, that's a reasonable answer. You guys see that? Like, that's worth something. Like, as an engineer, if your boss walks in and you're fiddling around with Taylor polynomials for this, they're going to be like, get out. You're done. You should have plugged that in the computer 2.5 hours ago. Cool?
Good.
Okay.